Hi everyone, so today we have a talk by Mert Ünsal, who's doing a master in data science, and he will present the connection between graph theory and linear algebra.
Thank you for the introduction. So hi everyone, today I'm going to make a very friendly, quick introduction to spectral graph theory. So there are two reasons I chose this topic. One is that I think it's a very beautiful and accessible example of how seemingly unrelated mathematical objects can relate to each other. And you only need basic linear algebra to understand it, so hopefully everyone who took their linear algebra 1 course should be able to follow the talk, and hopefully this should spark some interest into my research field. So what's spectral graph theory? Spectral graph theory is the idea of connecting these mathematical objects called graphs, which I will shortly introduce for those who don't remember, with matrices, and finding connections between the spectral properties of matrices and the combinatorial properties of graphs. And in particular, today I will focus on connectedness of graphs, which I will also define in a second, and we will see that eigenvalues of the matrices that we attach to a particular graph will tell us about how connected a graph is or whether it's connected or not. So okay, so let's get started. I will do everything in the blackboard. So chapter 1. It's going to be graphs and matrices. Maybe I can raise this a little bit. Yes, so who knows what a graph is here? I guess everybody's from computer science math background. Okay, so more or less everybody's familiar with what a graph is, but let's still define it. So a graph is, a graph, it's, when I think of graphs, I think of like the visual representation of them. So a graph could look something like this. It is something to represent like, it's a bunch of vertices and edges, and it's supposed to represent like some connection between things. So more formally, a graph is a set of vertices and edges, and what we can do is label these nodes, label these vertices, and then, for example, for this graph, we would look like 1 to 5. And the edges will look like, so there's an edge between 1 and 2, there's an edge between 2 and 3, and there's an edge between 4 and 5. So this will be the set of vertices and set of edges, and the reason I use the set notation here is that for the purposes of this talk, we're only going to focus on undirected graphs, so the edges here will not have any direction. So this is a graph, and as promised, I said I will do something with matrices. So now we're going to attach some matrices to this graph. So first matrix I would like to attach is called the adjacency matrix. We'll denote it by A, and it's going to live in Rn by n. And its entries will be Aij equals 1 if Ij is in the edges, and 0 otherwise. So this is actually how we represent graphs in computers. It's a sparse version of this matrix. So this is very standard. Anyone who did like graph algorithms on computers will have constructed such a matrix once. And then we also have our degree matrix, which lives in Rn by n. And this matrix will be diagonal. And its entries dii will be equal to degree of the vertex I. And the degree of a vertex is the number of edges that are connected to it. So for example, here the vertex 2 will have 2 edges connected to it, so its degree will be 2. And in terms of the adjacency matrix, we can write this as sum j aij. So for the vertex I, we are counting how many connections it has. So okay, this is some boring stuff. So let's move on to the interesting matrix, like which will be the main matrix we will be discussing today, which is called the graph Laplacian. And this is defined as d minus a. And this might seem a bit arbitrary in the beginning, and it looks a bit arbitrary, and when you first look at it, it doesn't really make all that much sense. But in the next 10 minutes, it's going to be a bit boring, but we're going to prove some properties about it. and you will see why this is an interesting matrix of choice. So what are these properties? So let's start with properties. So first of all, we see that we said we're dealing with undirected graphs. So the adjacency matrix here is symmetric, because if there's an edge between I and j, there will be an edge between j and I. And the degree matrix is diagonal, so it's also symmetric. And it's a linear combination of two symmetric matrices. So we have that LG is symmetric, which is one of the reasons why it's an interesting choice. And from our linear algebra knowledge, we know that symmetric matrices have real eigenvalues. So bear with me for the next 5 minutes. It's going to be like a bunch of results like this, but at the end, we're all going to need them to prove like the big result that we want to prove. So second property is that LG is positive semi-definite. And for those who don't remember, this means that X transpose LG X is greater than or equal to 0. So we're going to prove this. We're going to prove this property, and to prove this property, we're going to prove this following lemma. So we're going to prove that X transpose LG X is in fact equal to sum ij in the edges, I less than j, xi minus xj squared. So this immediately implies that LG is positive semi-definite because these squared terms are all greater than or equal to 0. So their sum has to be greater than or equal to 0. So okay, so let's prove this lemma. So first thing first, okay, so we'll just go from the definition, and this is going to be a bunch of steps, and there's one small trick at the end, but there is nothing actually complicated going on. So first, this inner product is going to be like xi, lg, xi. So I want to compute this term lg, xi first. So we have lg, xi equals d minus a xi. And, okay, dxi is going to be, d only has a diagonal terms, so it's going to be dii xi minus, and axi will be sum. This is just the definition of multiplication, aij xi. And we already saw that dai is actually sum j aij. So when we replace it with that here, we're going to get sum j aij xi minus xj. Everything good until now? Great. So now we're just going to do this x transpose lgx. So x transpose lgx is sum I xi and then lgxi, sum j aij xi minus xj. And then the trick here is to, okay, so it's unclear to how to go from this to this. So trick here is to see that for j equals I, this term is 0. And then we can separate the parts j less than I, j is larger than I. And then due to symmetric properties of A, we're going to get something nice. So let's do that. Sum I xi. And then we're going to get sum j is less than I, aij xi minus xj plus sum j is, can you see this? Oh, let's go here. Sum j, j is larger than I, aij xi minus xj And then the next trick here is that, okay, so we have this term here, like I is less than j, so we would like to bring everything to that form. So we have here that I is less than j, so there will be that part of the sum. So let's first write that part. Sum I is less than j, so this is like all combinations. We'll get aij xi minus xj. And then for the other sum, what we would like to do is this I and j, they are arbitrary indices that both go from 1 to n, so we can just swap them. So wherever we see I, we write j, and wherever we see j, we write I. So then here we're going to get, again, and if we swap those, then it's going to be I is less than j. So we'll get, so here we have xj now, AJI, which is just AIJ, since AIJ is symmetric, xj minus xi. Okay, this parenthesis is unnecessary. And then from this we see we have the term xi squared, we have the term xj squared, and then we have minus 2xi xj, and this is exactly the expression we wanted to get. So sum I is less than j, aij xi minus xj squared. So there's just two small tricks to get to this expression. And here we have the sum over the edges, but aij is 1 when there's an edge, and it's 0 when there is no edge. So this concludes the proof of this lemma. So what this lemma implies, okay, this was a bit of boring computation, but we'll get to some nice stuff later on. I just want to have everything rigorous. So this implies that all eigenvalues, so our matrix is symmetric posidefinite, so it's diagonalizable, so it's going to have an eigenvalues, and all eigenvalues are non-negative, since it's symmetric posidefinite, and so we know that they're real, and we know that they're positive, so the eigenvalues will look something like this. So this is a very, very nice matrix from a linear algebra perspective. It's just symmetric positive definite. That's like the paradise for the world of matrices. All right, so now one last boring result that we're going to need. Let's send this upwards. So I want to prove, we can bring this, okay. So I want to prove that also for this matrix that lambda 1, so the smallest eigenvalue is actually 0. So another lemma, let's say, lambda 1 equals 0, no matter what the graph is. And to do this, it's very simple. So we consider V to be the vector of all ones. And then when we compute LGV, we get that it's D minus A V. And let's look at the ith term of this matrix, of this vector. And this will be, we already proved up there, I think, it's sum j, aij, vi minus vj. And vi minus vj is, this is a 0 because it's a vector of all ones. So this is 0. So we found a non-zero vector that has a 0 eigenvalue. So the smallest eigenvalue of this matrix is always 0. So okay, I hope you bared with me until now. And this is like kind of like the end of boring results. So hopefully now we're getting to something nice. So I promised you that this matrix will actually tell us something about the combinatorial properties of the graph. And so far we just found a bunch of properties about this matrix. But now I want to understand, as promised, the problem of connectivity. So we'll go to chapter 2. Problem of connectivity. So let me remind you what is connectivity in a graph. So I think the best way to do this is just to give an example. So actually, I can just bring this down. So we see the graph here that we have. So a graph is connected if any two nodes are reachable to each other by walking through the edges. So for example, if we consider this graph, then any two nodes are reachable from each other by just walking through the edges. So there's a path between any two nodes. Whereas if you look at the graph above, we see that, for example, we cannot go from node 4 to node 3. So this graph is not connected, and the graph here is connected. And we would like to understand, can we look at this graph Laplacian matrix and tell whether a graph is connected or not? And in case it is not connected, we would like to know how many connected components are. As in, we partition our graph into parts where nodes can all reach each other. So for example, the graph here will have two connected components. The first one will be this 1, 2, 3, and the second one will be the 4, 5. And there's a very, very nice result, which will be like the main lemma of the talk today. So okay, so which will be the, maybe I can send this. Yep. So this is the main lemma of the talk today. So lemma. So we have that lambda 2. So we prove that lambda 1 is 0. And apparently it will turn out that the second smallest eigenvalue actually tells you whether the graph is connected or not. So lambda 2 is strictly larger than 0 if and only if G is connected. And moreover, a number of connected components will be equal to number of 0 eigenvalues of LG. So I think this is a very beautiful result. Like you can just so you're given a matrix, you're given a graph, and then you want to understand if the graph is connected or not. What you can do is you can use your favorite linear algebra package and find all its eigenvalues and count the number of eigenvalues to count the number of zeros in these eigenvalues to find the number of connected components. So this gives you a way of using the spectral properties of the matrix to find the combinatorial property of the graph. So we're going to prove this lemma. Everything good until now? Everything makes sense? All right. So let's go to the proof. So okay, so we can immediately see that the result below here implies the result here, because okay, so let's say there is only there's only one zero eigenvalue. This will mean that the graph is connected, and having only one zero eigenvalue means that the second one is larger than 0. So we're just going to prove that number of connected components is equal to number of zero eigenvalues of LG. So how are we going to do this? So we have our set of vertices, and if there are k connected components in this graph, this will mean we can write the set of vertices as a disjoint union of connected components. So for example, for this graph, S1 will look like 1, 2, 3, and S2 will look like 3, 4, and S2 will look like 4, 5, and those will be the two connected components. And then we're going to define these vectors. So these all one vectors, like, they turn out to be very useful. So in this case, we're going to have all one vectors, but for each connected component, we're going to have all one only in the vertices that are in that connected component. So let me define that rigorously. So we're going to consider U1 is to UK, and uij is, let me get this right, so it's going to be 1 if j is in SI and 0 otherwise. So this is just a formal way of writing what I said. And one thing to notice about these vectors, so these vectors are all in Rn, and one thing to notice about these vectors is that they're orthogonal. So why are they orthogonal? Because they have positive entries only in their connected components, and these connected components are disjoint. So when we take the inner product of these two vectors, wherever one of them is 1, the other one will be 0, and vice versa. So we have that ui uj equals 0. So let me explain this again. So we take ui, and we take the, let's say, the jth. Okay, so maybe let me use different terms here. So let's call this k. So let's say we take the jth element of this inner product. So if both of them are 0, we're fine. If one of them is 1, it would mean that the other one is 0 because the same vertex cannot be in two connected components. So this is why the statement is true. And furthermore, we have that LUI, this is equal to, as we proved before, sum ij in E xi minus xj, ui minus uj. And then this is also 0, because if there is an edge between two vertices, it would mean that they're in the same connected component, so ui minus uj would give 0. So this is 0 as well. So why did we do all of this? We just showed that there are a bunch of orthogonal vectors that are in the kernel of L. So this would mean that span of U1 to UK is actually a subset of the kernel of L. So what does this mean? This means that dimension of kernel of L is actually larger than or equal to k. So this span has dimension k, and it is a subset of the kernel, so the kernel should have at least dimension k. And why do we like this result? Because if we prove this, so the dimension of the kernel is actually the number of 0 eigenvalues, right? Because kernel is just all the vectors that give Lx equals 0. So the dimension of the kernel is the number of 0 eigenvalues. So it will imply this result, which I should have made precise before. So okay, and now we're going to prove like the other direction of this. So now we want to prove dimension of the kernel of L is less than or equal to k. And we're going to again use the previous results that we proved. So we're going to consider a vector in the kernel. And then we have U transpose LU, this we already proved as well, is sum ij in the edges, I is less than j, ui minus uj squared. So you need to bear with me here for a second because, okay, so we want to show that, okay, so this is equal to 0 because of the same argument, again, with the edges. And this would mean that, so if we consider the graph over there, so we see that anything that has an edge between them has the, so this implies that, let's take a second here. So this implies that since they are all squared terms, this means that ui equals uj whenever there is an edge. When there exists ij in E. And by induction, you can see that any other node in this connected component should have the same value as well. So if we consider this graph above, so this is a connected component, and we know that anything that is connected by an edge has the same value. So this is going to have the same value with this one, and this is going to have the same value with this one. So if you can walk through a path and all the differences are 0, this means that the value of the vector u in this connected component should be the same for all vertices in this connected component. So let's write this down. So for all vertices in same connected component, we have that ui is equal to uj. And what this means is that, okay, so what were these vectors ui? They were vectors that have all ones in the connected component. So what we can do is, let's say in a particular connected component, this u vector takes the value alpha I in the connected component I. Then we can write this vector u as sum of I alpha I ui. So if it takes value, let's say 3 in the connected component 1, we do 3 times the indicator vector of that connected component. And this means that this vector u lives in the span of these vectors, and this concludes the proof of D. So this is like just reverse of this statement. So this concludes the proof for the other side of the inequality. Does this make sense? Yes, so alpha here is the, so let's say u, so we prove that all the vertices in the same connected component takes the same value, right? So let's consider the connected component I, and let's say the vector u, it can be an arbitrary vector, takes the value alpha I in the ith connected component. So what was this ui? It's just all ones in wherever you have the connected, like wherever you have a vertex that is in this connected component, right? So if it takes the value alpha I in that connected component, you can just do alpha I times this indicator, and you're going to get that part of the vector. Great.
Maybe like, when you compute LVI, this is ij in SI times SI.
Sorry, where exactly?
Exactly where you were pointing.
Here?
Yeah.
Yeah, so this is ij in E, yeah. I forgot to put the E.
SI times SI, I think.
What do you mean by SI?
I mean, just
Oh yeah, sure, I mean, but okay. I mean, it's just going to be, like this is just from the definition, yeah? And then like this ui, uj, they are 0 whenever there is, whenever they're not in the connected component. So like things will disappear. Okay. So this was the main lemma. So, okay, so this gives us an algorithm immediately, as I mentioned. And people who come from computer science background might want to say, okay, why did we do all of this? We could just run like DFS, BFS, and find the number of connected components. Like, why did you take us through all this math? And you would be right. For this case, actually, it is kind of useless to do all of this because we know a lot simpler algorithms. But in general, actually, there are problems that we know to be NP hard, and we can find approximation algorithms for those using such spectral methods. So I'm going to give an example of one of these in the next part. But first, I need to clean the board. So in the next in the next 10. So this was all the heavy math we were going to do today. There's going to be really nothing more. Like now we're just going to do a lot of hand waving, and there's not going to be like any more computations. So hopefully you can just relax and look at just watch the board and do not follow. There will be no computations to follow, so you can just watch the rest of the talk a bit more relaxed, hopefully. Any questions so far, by the way? Okay, hopefully this board should be enough for the rest. Okay, so until now, what we proved was, given a graph, we can find out whether it's connected or not, and if it's not connected, we can find out the number of connected components it has. But even when a graph is connected, not all graphs are connected equally, right? So we're going to some chapter 3. I'm going to write this title later. But okay, so let's consider these two graphs. So we have this graph 1. And then let's say we have this second graph. So I would argue that this graph below is actually a lot more connected than the graph above, right? Even though they are both connected. So if we started, let's say, a random walk on this graph, we could get to any node very easily. Whereas if you start on this side, it's going to be hard to get to this side. And if you start on this side, it's going to be hard to get to the other side. So this graph, the nodes are not very well connected to each other. So we're looking for a way that we can distinguish between these two, the connectedness of these. So we're looking for a measure that can tell us, oh, this graph is more connected than this one. So if you considered, for example, this to be friend groups, in this friend group, everybody would know each other, and in this friend group, there will be two separate groups kind of like connected by just one friendship. So we would like to understand, when we get such a graph, how connected it is to another measure. So this is going to be the topic of the next chapter. So we're going to see that spectral methods, again, give us some nice methods to compute these, and we don't have classical algorithms to do such a thing. So there's this inequality called Cheeger's inequality, which is really, really fascinating and has a counterpart in differential geometry as well, on manifolds and everything. But today I'm just going to state like the simple notion of it. So again, to repeat, we assume that G is connected. And now I'm going to define this measure that I kind of like tried to describe. So I'm going to define it and then tell why it makes sense to define such a thing. So for a graph G, we're going to call this property conductance. So this is going to be denoted by phi G. It's going to be minimum over all subsets of vertices. This will make sense all in a second. I will stop and explain. Okay, so let me explain this like measure in a second. So we would like to understand, we would like to look at a part of this graph and see how unconnected it is from the rest of the graph. So this is why above the measure we're looking for is the number of edges that are going between S and S complements. So if we picked S to be this part of the graph, then the only edge that is going out of this part of the graph will be this one. So C, we can immediately see that this is a good thing because this part is kind of unconnected from this one, and there's only one edge in the middle, so this is trying to capture that. And on the other side, we are dividing by the size of the set S because, well, if you only picked one node, then the chances are that it's not going to be connected well with the rest of the graph anyway because it can have so many edges going out of it. So this is kind of like a normalization factor here. And we're considering minimum over such subsets, and we are considering only sets that are less than the size of the graph, where n is the number of vertices in our graph. We're considering only such subsets because if it was something larger, you could just like take the complement and it would come to the same thing because, okay, so if we just selected this one, number of edges that are going out of it would be the same. So this property, okay, it seems a bit arbitrary still, like this is some like heuristic on why it makes sense, but okay, so you can prove that a lot of properties of random walks on graphs and everything are actually related to the conductance of the graph. And in general, when we create like a random walk on a graph, if we wanted to converge fast, we want to have some high conductance. And there's this inequality called Cheeger's inequality, which I'm not going to. So one small remark is that in general, computing this conductance is NP hard. So computing phi g is NP hard. And so yeah, so we don't know polynomial time algorithms for this, but I will show by Cheeger's inequality that that actually you can get an approximation of this measure phi g using some spectral methods. And okay, so this is just Cheeger's inequality. We're not going to prove it. The proof is quite complicated, but the statement will be enough to get some insights. So we define this matrix LG. This is called the normalized Laplacian. So d minus 1/2 LG d minus 1/2. And we can define this d minus 1/2 since it's a diagonal matrix with all positive entries. And LG here is our normal graph Laplacian. And the Cheeger's inequality tells us that. I'll write in a second and explain. So Cheeger's inequality tells us that up to some square root of factor, the second smallest eigenvalue of this normalized Laplacian matrix gives us an approximation of this conductance phi g. So if we compute the second smallest eigenvalue of the graph Laplacian, we know that conductance will be somewhere between these two things. So this just goes to show that that spectral methods are actually useful in cases where the problem is NP hard and we can actually use spectral methods to find approximations of such optimization problems. And one final remark is that in general there are a few conjectures that originate from this idea that these spectral methods actually give us the best algorithms that work in polynomial time for many optimization problems. So this is very interesting, I think, and yeah, this is why I got interested in this in the spectral algorithms in the first place. And yeah, if you would like to talk more about Cheeger's inequality after, I'm happy to talk more in the apero. So thank you for listening.